Hello and welcome to this explainer video all about radioactive decay. Now there's quite a lot in this video, so I do recommend that you take your time, take notes, and if you're in my lesson, you might want to pause it, complete some of the questions, and then come back because we're covering quite a bit of content here. So let's start with radioactive decay. We know that whenever radioactive decay occurs, we will have the number of nuclei, the unstable nuclei, will decrease. So for example, if I'm looking at the decay of uranium-235 and uranium-235 is unstable, then what I'll find is that the number n of unstable nuclei will go down over time. And that's because that uranium nucleus has become something else. And we've done in some of my lessons exercises where we simply count the number of those nuclei, and we'll call that capital N. Now, on the graph, you can see what's called the characteristic shape of radioactive decay. And what we've done here is we've counted the number of undecayed, unstable nuclei over time. We begin with 80 and that decreases eventually, approximately after about 10 days, to around about 0. But as you'll notice there, not quite 0. Now, what this is called is exponential decay. And the nice thing about exponential decay is that even though it's complicated, it behaves sometimes in a predictable way. You'll notice here that I've drawn some lines on the screen which show when the number of undecayed nuclei, N, has become 40, and that's taken about 2 days. Now notice again, when I draw another 2 lines this time to go from 40 to 20, this takes another 2 days. And to go from 20 to 10 takes another 2 days. Now this time, 2 days, is referred to as the half-life. The half-life is the time taken for the number of undecayed, unstable nuclei to reduce by 50%. So notice we've gone from 80 to 40, reducing by 50%, took 2 days. We've gone from 40 to 20, took 2 more days, and then from 20 to 10, and that took 2 more days. Okay, so in this case, we would say that the half-life of the substance is 2 days. If another 2 days elapsed, we would expect the number of undecayed nuclei to be 5. Then we get to the point where it will halve again to 2.5, and that's where it's a bit dodgy, because can we have half of a nucleus? Don't worry about that right now. But the basic idea of the maths is there is that after every 2 days, in this case, we're going to have half and half and half again. Now, half-life is specific to the material. So I'm just going to show you some examples of half-lives here. If we had, say, for example, helium-6, that has a half-life of 0.8 seconds. However, we go to radon-222, 3.8 days, that's quite long. Compare that then with uranium-238, which is 4.5 billion years. Okay, so there's no guiding time for a half-life. A half-life could be anything from a very, very short time, seconds, even milliseconds, up to, well, as you can see there, billions of years. Okay, and those longer timescales are what we use for radioactive dating, and that's something we could maybe discuss in a future video. So this is all half-life. As I've said at the beginning of the video, there's quite a lot going on here, so you might want to pause the video at this stage and just have a think, take down some notes, and make sure that you're kind of happy with that. I'm assuming you're ready to go on. Let's just try, before we do move on, let's try another question. In this case, we've got here radioactive decay, we've got N, the number of undecayed nuclei, and we want to simply measure the half-life of this sample. It's a bit harder, this one, because the numbers aren't quite so neat. So why don't you, again, take a second to pause the video, have a look at the screen, think about what it is you would do in this situation, and then when you're ready, feel free to press play. Okay, I'm assuming you've had a chance to try. Let's have a look here. The obvious step here to go is to start, well, we start with 100. And so 100 divided by 2 after 1 half-life is going to be 50, and that's 50 in the middle there. So the half-life is going to be the time taken for 100 to go to 50. And we look there, and it's a little bit awkward. It's somewhere between 2 and 3. We're getting a little bit more than 2.5 Okay. Now, in this kind of situation, when we're not really sure, it's always a good idea to repeat the process. Okay. And this time, we're going to go from 50 to half, which is going to be to 25. So that's somewhere here. Okay. And you notice we get another line there of approximately the same width. It's good to see. That means our half-life is consistent. This question was designed so that the half-life is approximately 2.6 years. You can see that there, that after one half-life, we've got just over 2.5. All right. And after two half-lives, we've got just over 5. So that makes sense. 2 times 2.6, 5.2. And so that makes sense here. All right. Again, don't worry if you didn't get exactly 2.6. You may have got 2.5 or something closer. These values are approximate. They're not definite numbers, and they're really things that we measure in the lab. So don't worry if it's not exactly the same as the numbers that you see. And generally in exam questions, you'll find that they're quite nicely drawn, these graphs, to make it easy for you to make your measurements. Now, for our final part of this video, and again, feel free to pause at this stage if you want to take a break, is that sometimes you'll notice that we don't always have the number n on our graph. Sometimes you'll notice something else, which is A. Now, A is something called the activity. Now, activity is something slightly different. Activity is the number of decays that happen every second. If we think practically for a second, it's not possible for us to count the number of nuclei all the time. If we've got a radioactive source, that would be a very, very big number and impractical. But using detection equipment, we can measure the activity, and that's simply the number of decays every second. In other words, it's the number of nuclei which decay every second. Now, you'll notice there's some units. A is measured in what we call becquerels. This is the name of a French scientist, and we write that as BQ. And 1 becquerel is 1 decay every second. So if I'm saying to you the activity is 1 becquerel, it means that 1 nucleus decayed every second. Now, why is this important? Well, actually, A, the activity, and N have the same shape. This is called exponential decay. So when we're drawing these graphs, they'll actually have exactly the same shape. The difference will be the numbers on the y-axis. Okay, you may end up with different numbers on your y-axis because we're measuring different things, but their behavior is the same. And crucially, they will have the same half-life. Okay, so if you're measuring the half-life using A, it will be the same as if you were to measure using N. Okay, so the reason I put that in just at the end there is that I've noticed that a lot of questions do include the term activity in terms of decays per second, as opposed to this n. So you should expect to see either of those quantities. However, the process for finding the half-life is exactly the same. You simply measure the number on the y-axis, halve it, and measure the time it takes to get there, and then do that again just to check that you've got the same numbers, and then you should be fine. Okay? As I say, a lot to take in there, so please, especially if you're in my class right now, do take the time to ask questions, rewatch the video if you need to, take the notes, and crack on with any of the questions that you have. Thank you for watching.